Hi, and welcome back to another video. And in this lesson, we're going to learn about inverse functions. Now, what are inverse functions? What makes one function an inverse to the other function? Well, the main idea is that you're basically going to switch the x's and y's from one function. And once you do that, you get the inverse function. And that's the idea. And you're going to see they can present that to us in many different ways. They can give us points. We just switch the x's and the y's and that'll be the inverse. They can give us graphs. We're going to find what the coordinates are, then switch the x's and the y's. That'll be our inverse. And they can give us equations. You're going to switch the x's and the y's, and then you're going to solve for that y variable. You got to get the y by itself. So let's go ahead and just jump straight in. So taking a look at what we have here, it says to find f of g of x and g of f of x and determine whether the pair of functions f and g are inverses of each other. So, it says f of g of x. If you remember from the last video, that was fog and gosh, right? Remember where we plug one function into another, like f of g of x, like the way it is here. Basically, this is what we call fog, like f, that little o looking thing, and then remember this? So this is the notation from the previous chapter. They want you to find this right here, f of g of x. And it's going to be the same thing with the g of f of x. You're going to plug the f function inside of the g function, and that's goff, right? I don't know what you guys are calling it. But yeah, we basically find these. And if one of them is equal to a regular variable x, then they will be inverses of each other. So if the first one is x, then the second one is most definitely going to be x. So I'm going to show you guys that example right now. So let's go ahead and do it. So we have f of x, and let's use a different color. We have f of x is equal to 5x, and then we have g of x is equal to x divided by 5. So let's go ahead and plug one function into the other. How about we plug the g into the f? So we're basically going to find fog in this case. So what you do, we're trying to find f of g of x, right? So this right here has to go in here. So I'm going to write a 5. And when I write that 5, I'm going to leave a parentheses where the x is. So remember, here's my x, and I want to put a parentheses there and leave it blank so I can just plug something in there. And we're going to put the g of x function right in there. Just plug it right in. So now what do we have? We have 5 times x over 5. You can say you can cancel right now if you like, but let's go ahead and write it out. You have a whole number times a fraction that's going to be 5x divided by 5. And the 5's cancel, and you're left with x. Now, because you have an x, we know that these are inverses of each other. If you were to do the other way, if you were to plug the f into the g this time, so we're finding g of f of x. Remember, leave a parentheses wherever the x is so you have room to substitute. And we're going to plug the 5x in there, so put the 5x here. And take a look, the 5's cancel, and you're still left with an x. So f of g of x is x, and g of f of x is x, then it's safe to say that these are inverses of each other. So when I plug one function in, I got an x. When I plug one function to the other, I got an x. I already found this, I got another x. So it's safe to say that they are indeed inverses of each other. And that's the idea. And this is what we're going to be doing with the equations. So yeah, you can plug one equation into the other. And this is when they give you the second equation to work with. So we're going to keep going. Yeah, this is the same deal. I will do a similar so you guys can scope the algebra a little bit. So let me move this over here. All right, blank. Okay, so we're going to plug one function into the other. And it doesn't matter which one. If it works for one, if it works the first time, it's going to work for the second time. You can trust your mathematics a little bit, but you have to make sure you're doing it correctly. It's a lot easier. Another thing, it's a lot easier to plug your function into the function that has the fraction. Sometimes you can't help it. You may have two fractions, but I'm going to show you what I mean. And you know what? And who knows? The main idea is to just jump in. So let's just go ahead and jump in. We have 9. That is a G. We have 9. There are people who actually write their 9s as G's. You can go on check.com and see for yourself. So 9, and I'm not going to write the whole notation f of g of x stuff. We know we're going to plug one function into the other. All right, so we're going to have an open parentheses plus 1. So this is the first function with an open parentheses in place of the x, so we can just start plugging stuff in. So we have x minus 1 over 9. And then take a look. When you multiply 9 times a fraction that has a 9 in your denominator, you're going to cancel them out. You're left with x minus 1 plus 1. Negative 1 and positive 1 goes away, and guess what? You're left with x. So these two functions are actually inverses of each other. You know, just to be safe, let's go ahead and plug the 9x plus 1 inside the other function. So we have x minus 1, right, over 9. This is the g of x. So let's find g of f of x. Let's leave an open parentheses for where the x is. So that's open parentheses minus the 1 over 9. And we're going to go ahead and plug in the f function. So f of x, remember, is 9x plus 1, right? So let's plug 9x plus 1 right in there. And now there's nothing outside this parentheses, right? So you can imagine that we're going to take it out of the parentheses. So I'm going to just erase it like this. And now take a look at the numerator. We have a positive 1 and a negative 1. Those two cancel out. We have 9x over 9. 9x divided by 9. Cross off the two 9s, you know that will give you an x. So hey, if you get x for one, you're going to get x for the other. If you did the problem right. If you did the equations good. If you did the algebra correctly. Okay, so yeah, that's x. Then this has to be an x, and we already did the work. So they are inverses of each other. And you're going to see, we're going to speed along this time. And yeah, we'll do a similar question for this one. And sometimes no matter what you do, you're just not going to, you know, if it doesn't cancel out nicely, you're not going to get an x. Basically, they're not going to be inverses of each other, which, you know, spoiler alert, I know you just saw the right answer for the last similar question. But let's go ahead and let's find g of f of x. So we're going to find gof. And we're going to write it this way now. So we're plugging, remember, we go from right to left. We plug the f into the g. So let's plug the f into the g. I'm going to leave a big parentheses where the x was right here. So there's x plus 9 divided by 7. And let's plug the f function in there. What's the f function? The f function is 9x minus 7. So there's nothing outside this parentheses. There's nothing to distribute. So we're just going to have 9x minus 7 plus 9 divided by 7. And if you keep going, you know, add the like terms in the numerator, you're going to have 9x. Then negative 7 plus 9 is positive 2. And this is over 7. Now check this out. Nothing cancels, right? So because nothing canceled nicely like it did last time, hey, that's just gof, g of f of x. So we're going to put that as our answer. So we have 9x, then plus 2. And this is going to be all over 7. Oh, what did I do? What the heck did I do? That's 9x minus 7 plus 9. So positive 2. It says use integers or fractions for any numbers in the expression. 9x minus 7 minus. That's a positive 2. What did I do? I'm pretty sure that is here. It's over 7. And we're plugging, oh, because we found gof. All right, we found gof at first. We're going to save that. Don't worry. Let's find, they're asking us for fog, f of g of x, right? I completely forgot they were going to ask us for a double whammy. I thought we could do one or the other. Anyway, reading is fundamental, kids. So we're going to plug the g into the f, and let's do that really quickly. So let's make room inside of the f function. So we have the parentheses and then minus 7 like that. Let's put the whole g function in there. So that's x plus 9 over 7. And now, as you can see, the 9 and the 7 are not going to cancel. So we basically, there's nothing else for us to do but to distribute this 9 with the numerator. That'll be 9x plus 81 divided by 7. So remember, when you're multiplying a whole number times a fraction, you multiply just the numerator. We have the negative 7 hanging out over there. Let's go ahead and find the LCD of both sides. So this is over 1 technically, right? This is a 7, so you're going to have to find the LCD, which is 7. So you multiply the top and bottom here by 7. And we are running out of room, but we have 9x plus 81 minus 49 divided by 7. So I'm going to have to erase some of this stuff. Give me a second here. Yeah, that's better. We have 9x plus 2, so we should probably write that down, right? I will keep it right there. That's the first answer. All right, for our answer here, we have 9x plus 81 minus 49 divided by 7. So what is 81 minus 49? I'm going to use my trusty calculator here. So 81 minus 49, we get 32. So that's it. So this is 9x plus 32 divided by 7. And this was fog. You get the idea. Okay. So that's going to be our first answer. So it's really 9x plus 32 over 7. So let's go ahead and change that into a 32 by putting a 3 there. All right, nice work. Okay, g of f of x, we already found that. Let's put a fraction bar in there. That's going to be 9x plus 2 over 7. All right, nice work. Now, we didn't get a regular x like we did in the last question, right? So because we didn't get a regular x, these are not inverses of each other. And that's all there is to it. If it doesn't give you an x, it's not an inverse. All right, let's go ahead and do this one. It says the function f of x is equal to x plus 7. The function is 1 to 1. Now, what does that mean for it to be 1 to 1? Well, basically, for a function to be 1 to 1, they're basically saying that for every x, there's only one y. It has its own specific y. So, for example, if we have 1, 2, and then we have 3, 2, they both share 2. So because we have a number that's being shared, that's not going to be 1 to 1. And you remember back then when we were doing the vertical line test, let's say we have the x's stay the same, 1, 2, and then we have 1, 5. Because the x's are the same, this wouldn't even be a function. So, very quickly, let me go ahead and illustrate that for you. So, remember when we have 1, 2? So here's 1, 2 up here. Then we have 1, 5, right? Which is right above it somewhere here. When you run a vertical line through it, that is not going to be a function. So this wouldn't have an inverse because it's not a function in the first place. But they're not going to give you something that's not a function. They're all going to be functions. The question you're going to have to ask yourself is whether it's going to be 1 to 1. So when you're determining if it's a function, remember you do the vertical line test? Well, when you're determining if you have, let's make another random point, 0, 3, and let's do 4, 1. When you're trying to determine if it's 1 to 1, you do the horizontal line test. So let's go ahead and make a little XY axis here. Highest number is 4, so I'm going to do a 4 by 4. Okay, so let's go ahead and start plotting. We have 1, 2. We have 3, 2. So 1, 2, 3, 2. We have 0, 3. And then we have 4, 1, which is like right here. Now, you see all of these points right here? You can imagine if it's like a nice little graph connecting like this, something like that. Basically, you're going to do a horizontal line, a dotted line all throughout, something like that. And if it hits more than once, then it is not one-to-one. So you can do it here, you can do it here. It's only hitting once, right? Like it's only hitting once here, once here, once here. But right here, right to where those y's were equal at 1, 2 and 3, 2, it's actually hitting twice. So this is not one-to-one. Okay, so let's go ahead and finish up this problem like it was intended. What do we have here? They want us to just go ahead and find the inverse. They said that this function here is one-to-one. So if it's one-to-one, then there will be an inverse. And you're going to see, like even in your calculus class, a function may not be one-to-one, but you can make it one-to-one by restricting the domain, by chopping it up just a little bit. Okay, but anyway, here's how we find the inverse function, the nitty-gritty of everything. So basically, let's start off by saying that this is y equals x plus 7, because f of x is y, right? Like you can use them interchangeably, but for us, we want x's and y's to help us solve this thing. So, okay, we have y equals x plus 7. Now look at the steps up there. It says switch the x's and the y's, right? And then we're going to solve for y. So let's go ahead and start by switching the x's and the y's. We get x is equal to y plus 7. You see that? So wherever you see an x, you're going to put a y there. Wherever you see a y, you're going to put an x. So, okay, we did the first step. We switched the x's and the y's. But now what? We're going to solve for y. So to solve for y here, the y is almost by itself, but the 7 is stopping it from being isolated. So we're going to move the 7 to the other side by subtracting it so that it can cancel. So we're going to get x minus 7 is equal to y. Now we got the y by itself. So how about we write it differently? How about we say this is y is equal to x minus 7. Remember, the only thing I did was put the y on the left side. This is effectively the same statement, right? X minus 7 equals y, so y is equal to x minus 7, tomato. Now that you got the y by itself, you basically just created an inverse function. So to do that, you put a -1 here. You have your x. You basically change your y into f -1x. And you get x minus 7 still. So this is our inverse, x minus 7. So if you were to plot those, you would see that one is a reflection about the origin. And more than likely, they're going to give us one of those. Okay, let's do this one. Okay, so they told us that it's one-to-one. So it's going to have an inverse function. So let's go ahead and just jump right in. I'm going to go ahead and say this is y equals 3x plus 1 just to save some time. All right, so you know the two steps. Switch the x's and the y's. X is equal to 3y plus 1. Solve for y. Now, in this chapter, in this section, your ability to isolate variables, to isolate that y is really gonna be helpful. This is basically practice for that, because the hardest thing about finding the inverse when you're dealing with the equations is doing the algebra later. Everything about math, the hardest thing about math is the algebra, right? Even in calculus. Anyway, all right, so we have a 3 next to the y and we have a 1 next to the y. I want you to get rid of the 1 first, because remember, if you can save multiplication and division for last, if you can save division for last, save it for last, because you're going to end up with a fraction. Let's go ahead and get rid of this plus 1 by subtracting it. So you get x minus 1 is equal to 3y. Now to get the y by itself, you simply divide by that 3 that's being multiplied with it. Cross them out. You get y is equal to x minus 1 divided by 3. So remember, this is an inverse now, so I'm going to do a little trick here. I'm going to extend that, make that into an x, put an, you see how I did that? Like, that's the idea. We solve for y. As soon as you get the y by itself, and there are no other y's inside that equation, you just say that's f risen to the -1 of x, or the inverse of f of x. So fraction bar, x minus 1, and we're going to put a 3 there. And well done. And this is what we're going to be doing. So this is just a test of your algebraic skills for solving. All right, let's go ahead and do this one. I'm going to choose lime this time. So we have y is equal to x to the third power minus 5. Go ahead and switch the x to the y's. This is y third minus 5. We've got now we have a power. Remember, if you can add or subtract, go ahead and add or subtract. We're going to add the 5 to both sides. We get x plus 5 is equal to y to the third power. Now to get rid of an exponent, remember you take the root of that exponent. And make sure you take the root of everything. Don't just do them all separately. Whenever you're multiplying or dividing, you want to do everything as one. And also with exponents or with radicals, you want to do everything at once. So if you take the radical, the third root of one side, you take the third root of everything on the other side. So the third root of y to the third power is y. So I'm going to write it on the left. And this is equal to the third root of x plus 5. And we're done. Let's put a 3 here. And we have x plus 5. All right, fantastic. All right, yeah, I kind of spoiled the fun. Let's go ahead and solve it again. Okay, so what do we have here? We have y is equal to parentheses x plus 4 quantity cube. Okay, so you know what's going to happen. We're going to switch the x's and the y's. So this y becomes an x. This x becomes a y. You're going to add 3, raise it to the third power. Now we've got to solve for y. So remember, we can't just subtract the 3 in there because it's surrounded by a parentheses. You take care of the parentheses first, whatever's outside the parentheses. So we got to get rid of this cube by cube rooting both sides. So we're going to cube root the left and we're going to cube root the right. So on the left side, you're just going to get the third root of x. On the right side, the root and the radical, the power and the root, they both cancel each other out. So you're going to be left with y plus 3. And now the only thing left to get the y by itself is just to subtract the 3. So this is the third root of x. Remember, just don't write this as that, right? You don't want to put it underneath the radical. So it's the third root of x minus 3 separately. You're going to have that equal to your y. Now you can say that this is your inverse. So the inverse function is equal to the third root of x minus 3. And that's it. You're done. So, you know, practice those good algebraic habits. Knowing when to multiply, when to divide. If you have anything to add or subtract first, go ahead and take care of that first. And then leave the, what did I do? Third root of x. Okay, what did I do? Did I forget something? Let me see. We have x plus, it was x plus 4 the whole time. Let me go ahead and just every time. Why did I put x? What's going on with me? All right, I'm just going to erase all the 3s and just put a 4 there. Well, yeah, let's just go ahead and it'll be quick. 4, 4, 4, 4. You catch my drift. You get the idea. Maybe the cube threw me off. Every time I get these wrong, I'm like, what the heck is going on with me? Okay, now what do we have here? Let's go ahead and I'm going to hit similar. Let's see, get more help. Help me solve this. I don't need help with this, but that's just so we can reset it. Okay, it says the function, the 16th root of x is 1-to-1. So it definitely has an inverse. It says find an equation for the inverse. So we can find that right now. It says verify that the equation is correct by showing that plugging in one function into the other. So you see this right here. We have f, and then the inverse of the f is inside of the function f, right? You're basically plugging in your inverse. And remember what happens when you plug an inverse into its original function? You're going to get an x. So it's saying plug it in to make sure that they're both equal to x. And remember, you can plug the f function into the inverse as well. You can do back to back. But remember, if we plug one into the other and we get an x the first time, I'm not gonna lie to you, that's all you need to do. You don't have to do both. You can do both. You know, the more you do, the more math you do, the more precise your answer, the more precise your confidence in your answer. All right, anyway, let's go ahead and find the inverse of this thing. So we have y is equal to the 16th root of x. Let's go ahead and switch the x's and the y's. X is equal to the 16th root of y. Let's go ahead and get that y by itself. This line is kind of throwing me off a little bit. All right, so to get rid of the 16th root, you raise it to the 16th power. So that goes away, that goes away. You're going to be left with y, and this is equal to x to the, remember, this is just the parentheses, so you don't really need the parentheses. There's nothing sitting out here, so the exponent only is fine. So y is equal to x to the 16th power, so the inverse is equal to x to the 16th power. That was okay, right? Now, there's other stuff in here. So you see we have different domains for a, b, and c. We have the inverse of x equals blank, inverse of, right? But look at the right side. It says for when x is greater than or equal to 0, for when x is less than or equal to 0, or for all x. It's like, which one do we put? So we're gonna go over a couple things right quick. So you see the nature of our problem right here. We have the 16th power, the 16th root of x. Does that look familiar to you? You remember when we had something like the square root of x, like y equals the square root of x. And remember the graph, how the graph looks. And remember our table, we have so many, like we've come a long way, right? We start at 0, we have a 4, we just put perfect squares in there. 1 is technically a perfect square, let's put a 1. 1, 4, and then maybe a 9, right? You plug a 0 into here, you get a 0. You plug a 1, you get a 1. You plug a 4 into there, you get a 2. And you plug a 9, the square root of 9 is 3, right? So here are our points for this. 0, 0, 0, 1, 1, 4, 2, and then 9, 3 is somewhere way off there. But remember, we have a shape that looks like this. And remember, because this is a square root, remember, technically, there's an imaginary 2 in here, right? Whenever you have an even root, you cannot have any negatives underneath that radical. So what does that say about the x? Basically, the x here can be anything as long as if it's, remember we have square roots, we have to say that x has to be greater than or equal to 0, because you can plug a 0 in, the square root of 0 is 0, but you cannot have any negatives in there. So we have to say this has to be greater than or equal to 0, because if it's greater than 0, then it's positive, right? So looking at your graph, your x's will never go back towards this direction to your left. Your x's will only go to your right, so your x's will all be 0 or more. Now, we basically, it's the same idea with the 16th root of x. This is the 16th root. It's even. If it was an odd root, you can plug whatever you want in there, negatives, positives, you know. So if you have the third root of x, for example, remember the sideways snake from the last couple of videos, you will have positive and negative values. But because this is even, we're only allowed to put positive values in. So it's very similar to the square root of x. Now, I'm not exactly sure how does the 16th root of x look like. I have to put in my calculator and see. But that's the main idea. You know what? I have a calculator here. I just remembered. I can show you. So TI-84. Yeah, let me go ahead and okay, good. Let's go ahead and see how the 16th root of x looks like. So I'm going to go to y equals. I'm going to have to type in an x. And, you know, we could go ahead and put a radical in there. Let me see if we have the radical function. Okay, we have this right here. This allows us to put a 16 in there. And we're going to put an x right here. Let's go ahead and hit the graphing button to see, just get an idea how it looks like. Now, it's not doing it justice, but it's starting from all the way down here. And we're basically shooting across the sky, and it's increasing slightly. It looks very similar to our Nike check right here, right? And that's the idea. It starts from 0, 0, even though you can't quite see it. Maybe if we hit zoom, we can go into it a little bit more. But it looks like it's starting from, yeah, it's starting from 0. It's just very, very steep, but it's increasing, right? So that's the idea. It starts from 0, goes to infinity. That's your domain for the original, right? Now, what can we say about the range for our original? Now, the range starts at 0 as well, and it's increasing, right? Remember, range is going from, you're asking, what are your y's doing? Like with respect to the y-axis. It started from 0, and it's increasing, it's going up. So that's from 0 to infinity. So, yeah, so looking over here at the graphing calculator, so here's the 16th root of x zoomed in a little bit. We're going to just take all that knowledge and find the range. The range is from 0 to infinity. And let's see if we can figure all this nonsense out. And using this nonsense, I was about to say using this nonsense, using the knowledge that we have from here, we're going to use that to, I guess, answer all of these. So let's see, select the correct choice below. If necessary, fill in the answer box to complete your choice. So now these are the inverses. These are the domain of our inverses. So what is the domain of our inverse here? The x to the 16th power. So in order to figure that out, we have to, well, I'm going to need some more room first of all. So let's just erase all of this. Okay, so you can imagine having I guess you can have, yeah, you can have an XY table and you can start plugging in values, but we know that the domain for our original, so I'm just going to write domain here, is x is greater than 0. So from 0 to infinity. So we can say x is greater than or equal to 0, right? What is our range? The range was actually, remember, range is y, domain is x. Y is also greater than or equal to 0. We didn't have any negative y values, did we? So using this knowledge, and this is from our original, so let's put f of x here. It's like, how do we find the domain and range of our inverse? Well, remember up here, we said we're going to switch the x's and the y's. That's exactly what we're going to do here for the inverse. So I'm going to put inverse right here. So for the domain of our inverse, you're going to look at whatever your range is for your original, and you're going to change that into an x. So that will be x is greater than or equal to 0. For the range of your inverse, you're going to look at the domain of your original. The domain of your original had an x, and that's going to be our new range. So we're going to just replace that x with the y. Remember, that's the whole idea about this. You're going to replace the x's with the y's. Now, I know they're both 0, so it looks a little confusing right now, right? You may be really confused, but don't worry. As long as you keep this in mind that you switch the x's and the y's, you can't go wrong. So check this out. Y is also greater than or equal to 0, and that's what we're going to use. So just in case they ask you for, what am I doing? Just in case they ask you for domain and range, find a domain and range of the original, and switch the x's and the y's, and that would be the domain and range of your inverse. So which one do we use here? We said the inverse has to be greater than or equal to 0, so it's this first selection up here. And remember, we already found the inverse. It was x to the 16th power. So this is it. Well done. I know that was a long explanation, but yeah, inverses can be really tricky when you're factoring domain and range. We're just going to take what we learned from here and just move it right along. It says verify that the equation is correct. Okay, this is telling you to plug your inverse into your function. So the inverse we had was x to the 16th power. So let's put x to the 16th power here. And what do we get when we plug it in? I'm not even going to do the work. We know we're going to get an x because we've already done the word previous, so there's no sense in going over again. So remember, whenever you plug a function into its inverse or the inverse into its original function, you're going to get an x. This is asking you, see, we have f negative 1 parentheses, f negative 1, the function. So what is the function? The function is the 16th root of x. Remember, that was the original f of x. Just put that in there. So 16th, we have an x, and we should get an x right here because they are inverses of each other. Nice work. Yeah, save yourself some time. The equation is verified. Yes, it is. It better be. All right, good job. All right, moving right along, we're going to do the same thing for this one. Take a look at this domain here. This is saying that x, we have x minus 5, right? So x cannot be equal to positive 5. Remember that chapter? So I don't think they're going to ask us for the range. What about the range, though? You can use a graphing utility to, like, use a TI-84 maybe to graph it, but I know we don't quite have time for all of that. But let's just go ahead and jump in. So what is the inverse? Well, you know what? Before I even find the inverse, maybe we should just go ahead and find a domain and range. It's like the elephant in the room here. So we have y is equal to x plus 20 divided by x minus 5. Okay, so for your domain, remember you set the bottom equal to 0 and solve for x. You get x cannot be equal to 5. So I'm going to put domain just like that. Now, what about the range? I'm not sure what your professor taught you guys about the range, but we have 3 techniques, and it all depends on what the power of the numerator and the denominators are. So looking at the numerator and denominator here, we're going to have 3 cases, and I hope they don't keep doing this to you guys, but you're going to see there's only 3 cases you have to worry about. And you're going to basically compare the highest exponent with the numerator and the highest exponent of the denominator. The highest exponent of the numerator here is a 1, right? Technically, the x is risen to the first power. And the highest power of the denominator for the x is also a 1. So basically, you're going to go ahead and divide by the you're going to go ahead and divide the top and the bottom, basically. But it's like, divide what? All you do is divide the number that's in front. So what number is in front of the x? Remember, there's an imaginary 1 technically. And this is for when the powers are the same. Or I should say the degrees are the same. Remember, power, degree, the definition of degree is highest exponent, right? So we're going to say degrees, or we're going to say same degrees. So because we have the same degrees, we divide the coefficient of the top over the coefficient of the bottom, and we get a 1. So the range is going to be that y cannot be equal to 1. So, and that's it. So what you're going to see, they're going to give us maybe 2 more examples to go on top of that. If they only give you this when the degrees are the same, the power on top is the same as the power on the bottom, then we're going to run with that. We're just going to divide the coefficients and call it a day. And that would be where the graph is not going to touch for your y. Okay, we got the domain, we got the range. So we can figure out what the domain and range of the inverse is. And we'll take it from there. Okay. So let's see what we got here. All right, so let's go ahead and find the inverse of this guy here. Okay, so what do we have? Well, what's the first step? First step you're going to do is to switch your x's and your y's. So that's x is equal to y plus 20 divided by y minus 5. So far, so good. Now we have a fraction. I don't like fractions, do you? So to get rid of this fraction, how about we multiply both sides by the denominator? And you're noticing I'm putting it in parentheses because we're going to multiply with the x as well. Let me make sure you guys can even see this, what I'm doing. Okay, you can see. Okay, so to get rid of a denominator, to destroy a fraction's denominator, you multiply both sides by that denominator. So you're going to multiply this side by y minus 5, and you're going to do the same thing over here, y minus 5. These will cancel, so what are we left with? We're going to come up here now. We have y minus 5 times x is equal to y plus 20. We're almost there, I promise. Let's go ahead and distribute the y. Remember, we're trying to get the x's and the y's to one side. Let's go ahead and distribute everything we have here. This is like a reverse distribution. You could have put the x in front if you wanted to, but you can distribute this way. So we have y times x, which you know is xy or yx. Most people like to see xy. Then we have distribute negative 5 times x is negative 5x. And this is still equal to y plus 20. Now what? We got to get the y's over to one side. And if it doesn't have a y, bring it to the other side. So if it has a y, I'm going to bring it to the left. If it doesn't have a y, I'm going to leave it to the right or bring it to the right. So let's bring this y that's over here over to the left by subtracting it. And this negative 5x it doesn't have a y, so let's add it. Let's add it to both sides so we can get rid of that. So you're going to see those cancel, these cancel. So we have x, y minus y is equal to 5x plus 20. And this right here is the hardest type of inverse problem because we had a fraction and we have y's in different locations. So this is as tough as it gets, by the way. This is the toughest part of the whole section. So if you can get over this, if you can handle this, you'll be okay. But the last step, we have a y in two different terms, right? Factor it out. This is what's going to separate the men from the boys and the women from the little girls, okay? Whenever you have two y's like that in two different terms, you factor it out. It's a GCF. So you're going to have x minus 1 is equal to 5x plus 20. We're almost done. Let's go ahead and divide both sides by the x minus 1. And we are done. So the inverse is going to be, so I'm going to write it up here in green. The inverse is going to be 5x plus 20 over x minus 1. Yeah, that was a tough one, right? Okay, but at least we found the inverse of everything. So what about the domain and range? Well, the domain here, we can actually figure out the domain by setting the bottom of our inverse function equal to 0 and solving for x. And you get x cannot be positive 1, right? This is for the domain here. And check this out. Didn't we technically have something like that similar? Didn't we already find the range of our original? Why it cannot be equal to positive 1? So, it's like we can find the domain of 1, and if we find the domain of 1, we can get the range of the other by just switching the letters. So, we're going to do that next time. Rather than have you memorize this whole degree stuff with the dividing and stuff like that, we're just going to find the domain of our inverse function and say that's the range of our original, just in case they ask us for that. But it looks like we're okay for right now. So let's go ahead and oh, the range. The range, I'm gonna, because I know these are inverses of one another, the range, I'm just gonna replace that with a y. So y cannot be equal to 5. So just in case they ask us for domain and range, we'll be ready. And they do ask us for domain, so let's go ahead and jump in. As we progress, it's going to be a lot smoother, I promise. I just had to give you the preliminaries and show you where it's coming from. And you're going to see we're going to use the shortcut way. Because if you haven't noticed so far on my channel, I like to use a lot of shortcuts, and we end up getting them correct 99% of the time, right? Anyway, so x cannot be positive 1 for our domain, so we got to choose this one with the cannot equal to symbol, and we're saying it's going to be a 1. So the inverse that we found is going to go in this box, and so we have 5x plus 20, and this is all over x minus 1. Well done. All that work. Okay, so the inverse function is inside the parentheses. So what is the inverse function? Is what we just got a little while ago. 5x plus 20 over x minus 1. And when you plug an inverse inside the original, you should get an x. Let's go ahead and put an x here. We know it's going to be an x. This right here inside the parentheses is going to be the original function, which is this guy up here, x plus 20. And this is going to be all over x minus 5. Excellent. Yes, it's verified. It's always going to be verified. Okay, next, moving right along. Okay, now the headache with the equations is gone for now. Now we're going to start doing things that are more graphical. So let's just obliterate all this and start fresh. Okay, so does the graph represent a function that has an inverse? So whenever you're given a graph, you want to go ahead, and I wish I can draw over the actual, I'm sure there's a way to draw over the material that we're given so I don't have to keep going over to this app over here where I have to draw, but I'm just gonna show you guys something. Okay, so I'm gonna just give a little rough sketch. It looks something like this, like you have a little horizontal line like that, right? Then it goes up like this, and then it ends something like that, right? Something like that. So, how do we know if it has an inverse? Well, it won't have an inverse unless it's a one-to-one function, right? So if it can pass the horizontal line test, we're good. As long as it hits once each and every time, we're good. So you can imagine a horizontal line going through here. It's only hitting once. But if you run a horizontal line through something that's already horizontal, it's going to keep on hitting over and over, and you don't want that. So does this have an inverse? No, because it does not pass the horizontal line test. And that's what we're going to do here. So take a look at this. We have a little squiggly, for lack of better words, we have a nice little curve. It looks something like this. Like, something like that. You don't have to be perfect. And if you run a horizontal line through it, will it hit more than once? Absolutely. It hits here, shoot, more than twice. So because it doesn't pass the horizontal line test, this is a no. Okay, determine whether the function has an inverse. So look at the shape of the graph. There are two ways that you can do this. You can do the horizontal line test like we've been doing, right? It's tried and true. So you have a little, I'm going to be a little ugly here. All right. So we have a little, little graph that goes like from here to here, right? Something like that. I don't know. If you run horizontal lines through it, will it hit only once? Yes, it does. At every single part of the graph, it only hits it once. So this answer is definitely yes. If you wanted a more, I know the rough sketch stuff has been great to us, but if you wanted to be sure, you can actually pick a point out from the graph. So let's go ahead. Give me 1 second. I want to do something. If we have homework, I'm going to go to properties, capture cursor. Okay, I just want to make sure. Okay. So let's go ahead and, pick out some points from here, and let's see if when we pick a point and we switch the x's and the y's, will it give us what we need? Will there be a corresponding point waiting for us? So let's go ahead and pick a nice solid point from here. We have -3 comma. It's not quite solid. Let's pick something more. We have 0 comma -1. I think that's 0 comma -1. We're gonna see. So we have 0 comma -1. It will be right here, right? Let's go ahead and switch the x's and the y's. So this is my switching notation, I guess. And let's see what the new points of this will be. So instead of 0 comma -1, we're going to put a -1 here and a 0 there. And do we have something like that on the graph? -1. We got something very similar. It's a little off, but I think it's safe to say that, yeah, this will have a inverse function. It would be like, right, you can see -1 comma 0. It's not going through it, but this is a little bad example. Hey, it passed the horizontal line test. That's all that matters, I suppose. Let's see, use the graph of f to draw the graph of its inverse function. Now, when you're generating a brand new graph, you want to make sure you get the points from the old graph. So we need some solid points. And what I mean by solid is that it's right on the, like right on the corner. Like you see this, for example, you see they give us a little point. This is 1, 0. So you know what? Let's go ahead and write, let's go ahead and write down those two. So we have 1, 0 for one solid point. And what's another solid point? We have 2, 6. Let's write that down, 2, 6. Let's find the inverses of both of those points, and that would be our new function, our new graph. So remember, to find the inverse, you switch the x's and the y's, right? So to find the inverse, this becomes that, that becomes that. This becomes a 0, that becomes a 1. Switch the x's and the y's. Instead of 2, 6, you're going to have 6, 2. So these new points are going to be part of our new graph. So let's go ahead and reflect that. So we're going to click to enlarge. Now, all you do, you take this line tool, because they use the line, right? You take this line tool and you go to the 2 points that you just made by switching. So we have 0, 1, and we have 6, 2, 1, 2. And check this out. This right here, they are definitely inverses of each other. And if you're not 100% sure if they're inverses of each other, right? So I'm going to do a little rough sketch here. You know, we love our rough sketches. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, I'm going to use a little, I guess, purple or little pink graph. So we have 1, 0. We have 2, 6. And there's like a straight line. I can make a straight line. Let me see. Yeah, like something like that, right? So that's a straight line going from there to there. And let's go ahead and use the alignment, plot the other ones. We have 0, 1, which is right here. We have 6, 2. So 1, 2, 3, 4, 5, 6, 2, like that. And I'm going to do the same thing, just going to make a line going straight through like that. Now, if you're wondering if your graph was 1 to 1, draw a dotted line going straight through the origin at a perfect 45-degree angle and see if it's going through the 2 points, the 2 graphs, like right down the middle. See if they're mirror reflections of each other. And yes, they are, aren't they? You have this arrow is like a mirror reflection of this. You have this long arrow as a reflection of this long arrow. And yeah, these are definitely inverses of one another. So if you ever, you know, generate a graph and connect the points, and connect all the dots and make some rough sketches, or some actual sketches, I should say, run a line going straight through the origin, straight through the middle, just like that, like the white line, and see if it creates a mirror image of the other one. And the answer would be yes, they are inverses of each other. So let's hit save, check answer, got it, fantastic. Good stuff, right? Good stuff, good stuff. Okay, use the graph of f to draw the graph of its inverse function. So we're gonna have to get our hands on a couple points there. So you know what? Let's go ahead and do something. Let's do something slightly different. We want to make sure that this blue line here is agreeing with all the blue lines inside the original problem. Okay, and they are. All the dotted lines are the blue originals. So which one of these looks like an inverse? Well, let's go ahead and pick out some points. We need solid points. We need solid evidence. So let's go ahead and write them down. We're going to have, looks like we have 0, 1 for 1 point. So 0, 1. And then we have 2, 1, 2, 3, 4. So 2, 4 for the other. And we're going to find the inverse by switching the x's and the y's. So let's do that. So instead of 0, 1, we're going to have 1, 0. Instead of 2, 4, we're going to have 4, 2. So both of those points should be on the new graph with a nice little curve going straight through. And let's see which one of those would give it to us. So we have 1, 0. So we better have a 1, 0 for the new f of x, for the f of negative 1 of x, the inverse. Do we have 1 comma 0 here? No, we do not. It's completely blank. So we don't have a 1 comma 0 right there, so that can't be it. What about here? Yes, we have 1 comma 0 here. Now, let's make sure that we have our other points. So this is 1, 2, 3, 4, comma 2. No, not quite. It's not there, so it can't be choice B. What about this one? We have 1 comma 0. Nah, we don't have 4 comma 2, do we? Let's go to this one. Oh, wait a second. Did I mess up? Let me see. 0 comma 1. Do we have? Why did I say 4 comma 2? This is 2 comma. Oh, no. The original is 2 comma 4. The inverse would be 4 comma 2. Yeah, I'm good. What the heck is going on? Then we have 0 comma 1. So that'd be 1 comma 0. I think, maybe we should choose maybe a triple point, because I'm kind of somewhat confusing myself here. You see where I have the arrow right here? Let's just add another point to this, just so I can be 100% certain that we have negative 6 comma negative 1. And I know it's not solid, but it's going to give us the idea of how it should look like. So negative 6 comma negative 1. When you switch the x's and the y's, you're going to get negative 1 comma negative 6. So we're going to put that as another one of our points. Remember, the more points, the better. Wait, did I say this one doesn't? This is 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4. I know what's going on. This point right here was not a solid point, was it? Like if we go back to the original here, this is not 2 comma 4. This is like 2 comma 3.5. So I know I really just wanted to be solid, but this is 2 comma 1, 2, 3 and a half, right? So we're just gonna change that into 3 and 1/2. I see what happened. I wanted it to be 4 so bad, but no, this is 3.5. So it's okay. I promise. We'll just change that into 3.5. And we're going to do the same thing with the other one. So this is even more precise. So I promise we're going to get it right this time, okay? So let's see. Do we have 1 comma 0? Yes. Do we have 3.5 comma 2? So we'll go 1, 2, 3.5 comma. Yeah, this is it. And do we have our optional point, the negative 1 comma negative 6? So we have negative 1, negative. Yeah, got it right there. So this is definitely the answer. So yeah, even pros can make mistakes too. Well, we got it right, but I slightly misled myself. You want to make a nice little estimation if it's not solid. I thought I could have sworn that this was a solid point, but it's not. It's not 2 comma 4. This is 2 comma 3.5. But man, shoot, we still handle business. Okay. All right, let's go ahead and jump in. Given the function 5x minus 9, what is the inverse function? The inverse function, as you well know, requires us to switch the x's and the y's and then solve for y. So this is x is equal to 5y minus 9. We switch the x's and the y's and let's solve for y. So we're going to add the 9 to both sides. You get x plus 9 is equal to 5y. Divide both sides by the 5 to get the y by itself. You're left with y is equal to x plus 9 over 5. And we just found the inverse, so I'm going to sneak this in and change that into inverse notation. You don't have to do that. I'm just trying to save paper, or I'm trying to save some space. Okay, anyway, there is the inverse. So let's go ahead and type in the inverse. So we have x plus 9, and this is divided by 5. And there we go, fantastic. Okay, so they basically put both of these graphs on there, and very interesting. We're just gonna go ahead and graph them separately. There's a couple ways we can, because these are nice little straight lines, we can just use 2 solid points and just switch them, and that would give us what we need. So what are the 2 points? Well, Let's go ahead and take it back to basics. Let's graph the first one. The first one should be in red. Remember, the dotted one is always in red. Oh, no, it's not. It's not. Oh, they mixed it up. They messed it up completely. They didn't even tell us which one is which, but it's okay. We're just gonna go ahead and start by graphing, and we'll take it from there. So where did we begin? Where could we begin? We can just go ahead and make an XY table. So give me 1 second. Let me erase all this. So you know what? We can make our own points. All right, this would be your f of x. And the beauty about making your own points is that you can choose whatever you like. And we're going to do the same thing for the inverse as well. So how about we plug in 0 for x and then 1 for x and see what we get. And let's see. So you plug a 0 for your x. F of x is equal to 5x minus 9. You plug a 0 in there. So 5 times 0 is 0. 0 minus 9 is negative 9. Put your negative 9 there. Plug a 1. 5 times 1 is 5. 5 minus 9 is negative 4. These are definitely points on your graph. So let's see if we can line that up first. Let's see if we can find 0, negative 9 and 1, negative 4. But you know what? Since we're here, let's go ahead and find the inverse while we're at it. The corresponding inverse points. So remember, this corresponds to x plus 9 over 5, since we went through all the work to figure that out. And now instead of plugging stuff in here, which you definitely could, you want to be careful because you're going to end up with fractions. And if the numbers don't mesh well, you don't want to have fractions. Okay, but we can go ahead and do our little inverse trick because we know this is the inverse of that one. We're going to switch the x's and the y's. That'll be negative 9, 0 and negative 4, 1. Easy peasy, right? Let's see if we can figure out which one. Oh, it does say that the inverse is the dotted line. So they switched it up on us. So the blue line should be our original. So let's see which one of these lines has 0, negative 9 for the original and 1, negative 4. So yeah, there's 0, negative 9. And do we have 1, negative 4? So here's positive 1, 1, 2, 3, 4. Yeah. So this is definitely the original graph. And now let's see if the inverse is also going to correspond to it. So the inverse says we have negative 9, 0. So let's go to negative 9, 0. Yep, there's negative 9, 0. And what about negative 4, positive 1? So negative 1, 2, 3, 4. Yeah, this is definitely it. And another thing, if you were to run a dotted line across the origin at a 45-degree angle, would you go through both of them? Yes, you will. It's like a mirror image of one another. So we are done. That worked out nicely, right? And you notice we didn't do any rise over run stuff. We just plugged in our own values. We plugged in at 0, plugged in at 1. You're free to do that because the domain is all real numbers. There is no fractions or square roots in the original, so you can go ahead and plug in whatever you want. State the domain and range of interval. Yeah, I was just saying it, right? So look at your original function, 5x minus 9. There are no square roots. There are no fractions or anything like that. So this is all real numbers. So the domain in interval notation will be negative infinity to infinity. Remember, domain describes your x. Let's put an infinity right there. And then you can look at the graphs. So for the original, which is f of x, you see the x's keep decreasing as you go to the left. As you go to the right, they're increasing. So yeah, negative infinity, positive infinity. And the range describes your y. So you can see, yeah, it's going all the way down, going all the way up. So yeah, this is infinity all around, negative to positive. Okay, what about the inverse? Well, if your original domain was negative infinity to positive infinity, then the range of your inverse would be the same, negative infinity to positive infinity. And remember, I want to stress that the domain of one is the range of the other. The domain of your original is the range of your inverse. The range of your original is the domain of your inverse. So you see I'm going in a crisscross pattern here. The numbers could have been different, and this is how you want to do it every time. Next question. That was a doozy. All right. They're gonna make it just a tad more difficult, but we can get through it. Okay. Given a function. All right. Let's go ahead and find the inverse. Now, note they said that x has to be greater than or equal to 0, didn't they? That's the domain. So the domain of our original is going to be the range of your inverse. So let's see what we can do. We have y equals x squared minus 2. We'll focus on the domain in a second, but let's find the inverse. So switch the x's into y's. This becomes an x. This becomes a y minus 2. Let's solve for y. Get rid of the 2 that's sitting around. So you get x plus 2 is equal to y squared. Take the square root of both sides to get rid of the square. Remember, do everything, not individually, but everything. You're going to get y equals x plus 2. And the x plus 2 is being square rooted. This is your inverse now. So let's write the inverse in this form. And we have a radical. Interesting. Okay, so the original is y equals x squared minus 2. The inverse is the square root of x plus 2. So let's go ahead and type that in first. So x plus 2. Excellent. Now, now how do we graph this thing? Well, one step at a time. So it's really nice that they gave us the domain of the original. They said that it was x is greater than or equal to 0. So I'm going to go ahead and erase the work I just did for inverse for a second. And while I'm at it, I'm going to change that into an f of x, which is what it was originally, right? Before we changed it to a y. So it's like, what does it all mean? What does any of this mean? Well, let's start off by making an XY table. We're going to use more numbers this time. The more numbers, the better. Okay, remember they told us that the domain is x is greater than or equal to 0. If it's greater than or equal to 0, that means 0 is your starting point. You're going to start at 0 and ask yourself, okay, what else is greater than 0? Well, for your x, right? So 1 is greater than 0, and 2, and 3, and 4, and so on. So these are the x's that you're going to plug in, which means that you're going to get some y's out, right? So let's plug what we got for x, our allowable x's, the acceptable x's based on the domain, and plug them in to get our y's. So plug a 0 in, it'll be 0 squared, which is 0. 0 minus 2 is negative 2. We have 1 squared, so that's 1 minus 2, which is negative 1. 2 squared is 4. 4 minus 2 is 2. 3 squared is 9. 9 minus 2 is 7. 4 squared is 16. 16 minus 2 is 14. And you can see that this right here would be your graph. So once we mark those up, we'll be done. Let's go ahead and see if they're going to let us slide with this one. So we're going to look for 0, negative 2 at least. Let's open up the first one and see if we find 0, negative 2 for our original. Notice we didn't even touch the inverse yet. So do we have 0, negative 2? No, we don't. Anywhere, not for the red nor for the black. Did they at least tell us which one was which? No, they did not. I think maybe the black may be the original. I don't know. We're going to keep going. Now, do we have 0, negative 2 here? No, we do not. Here's the point 0, negative 2, but there's nothing touching it, so it's not going to be B. What about here? Nope, there's nothing touching it. It's interesting how that works. What about here? Yes, this is the only one that has 0, negative 2 going through it. What about 1, negative 1? There it is. What about 2, positive 2? There it is. So all these points are corresponding. And what about the inverse? So remember, with the inverse, if you got your hands on your original, and we got that by, considering the domain here and plugging in what's allowable, we plugged 0 and everything greater than or equal to 0. 1, 2, 3, 4, right? So for the inverse, it's the same deal. You're going to go ahead and switch the x's and the y's. That'll be negative 2, 0, negative 1, 1, 2, 2, which doesn't do anything, right? 7, 3, and 14, 4. Let's see if these points are going to, show up on our other graph. Yep, negative 2, 0, negative 1, 1, 2, 2. Yeah, got them all. That's it. We are done. It has to be D. And you're going to see, we're going to do something a little crafty. We're going to base our answer on the domain and range. Okay, so what is the domain of F? The domain of F is equal to the range of the inverse, right? We know that. So it says state the domain and range. Okay, they want interval notation. So what was the domain of our original? They told us from the get-go. X has to be greater than or equal to 0. So wouldn't that just be a bracket with 0 all the way to infinity? Okay, so if you forgot about the interval notation stuff from a few videos ago, where have you been, man or girl? So this is for x is greater than or equal to 0. So if x is greater than or equal to 0, you're going to start off at the 0. And it's equal to 0. So let's shade what is to the right of 0? What is greater than 0? Everything over here going off into infinity, right? So we know we're going to shade to the right, but what symbol do we use? Because it's equal to, we use a bracket, a square bracket. In interval notation, you can think of it as a copy and paste type of thing. Interval notation, you take whatever your graph is with the symbol. So we start off with a bracket at 0. So that's from 0 all the way to whatever that is, infinity. So that's our interval notation. Just a little refresher. Okay, what is the range of your inverse in the domain of your original? I'm sorry, what is the range of your original and the domain of your inverse? So here we're gonna do something a little, let's take a look at the graph that we got. They're asking us, what is the range of your original? So let's focus on the black line. The range of your original, what is your y start off down here? The y start off is negative 2. And it seems like it goes all the way up to infinity. So it's safe to say that the range of your original is negative 2 to infinity. Well, if the range is negative 2 to infinity, then the domain of your inverse has to be negative 2 to infinity. And is it? Let's test it out. Do your x's start at negative 2? Yes. From left to right, it starts at negative 2. Does it go off to infinity to the right? Yes, it does. It keeps going to the right. So this is definitely inclusive. Negative 2 to infinity. And if you were here for my earlier videos, you would know that my bracket and my parentheses on my keyboard look alike. I haven't made that mistake in a long time, but yeah, it's kind of messing me up. All right, anyway, so ready to do another one? So we're going to do the same thing, same routine, and let's go ahead and get through this. Let's do it. Okay, given the function x cubed minus 12. Now, with the x cubed functions, remember that they look like snakes, right? So it looks something like that. And one of the properties of the snake, and the sideways snake as well for the radical 3, the third root, the domain and range is negative infinity and positive infinity for both, okay? So believe it or not, that's going to make things easier for us in the long run, because if the original is negative infinity, positive infinity for both domain and range, then the inverse is going to, when you switch the x's and the y's, is going to be the same exact thing, negative infinity, positive infinity. So let's go ahead and see if we can find the inverse, which we will. Okay, so I'm just going to go ahead and write y is equal to x cubed minus 12. So let's switch the x's and the y's. You get x is equal to y cubed minus 12. Let's add the 12 to both sides. X plus 12 is equal to y cubed. Let's take the third root of both sides. We get the third root of x plus 12 is equal to The third root of y to the third power is just y. They cancel. Okay, and yeah, just so you see what I did, I took the third root of both sides, okay? And that's how I got this. Okay, so that is your inverse. You got the y by itself, so everything to the other side of the equation is your inverse. So the inverse looks like this. And that is the third root of x plus 12. Okay, so we have everything we need. You know they're going to make us graph it. Let's go ahead and put the third root of x plus 12. Good job. And now we're going to graph this thing. All right, so let's see which one is which. Look at this mess. It's a huge mess. So remember this, the snake looking graph starts like this. Something like that, right? And we do have the snake, which is y to the, remember this is just y is equal to x cubed. That's what this graph is. Now we have a minus 12 over here. So you're basically going to shift down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you're going to have a snake down there instead. All we did was shift vertically down 12 units from the previous video, from my transformations video. It was an awesome video. So we should have a snake that's down that way. And let's see if we have something that corresponds to it. You see the middle of the snake, like the middle of the snake body is right on the axis. So it looks like it's going to be A, definitely, because I'm looking at the other ones, and you can look at the other ones. We don't have a yeah, look at this one. It's just perfect. That's exactly what we have. It's going through the negative 12. This is negative 12 down here. Yeah, that's got to be it. If you were to do the same thing with the sideways snake, yep, it's negative 12 but on your x-axis this time. So if it's going through your y-axis at negative 12 for your original, it's going to go through your x-axis at negative 12 for your inverse. And that's just looking too good to not be true. Yep. So you see, I didn't even make an XY table, but you definitely can. You can plug in whatever you want. You can plug in -1, 0, 1, 3. But from negative infinity to positive infinity is up to you. So yeah, snakes, anything with a third root or a third power, you can write this down in your notes. The domain and range will always be negative infinity to infinity each and every single time. Same thing for this one. Fantastic. Okay, looks like what do we have? Only one more? We're soon going to find out. Okay, so given the function f of x is equal to x minus 4, they want us to find the inverse, graph it up, and give the domain and range. So they weren't nice enough to, they didn't give us the domain and range last time. And look, they were even nice enough to give us a little hint. Basically, in order to solve, when you raise a root to the same power that has the same number as its index, like the third root of y, when you raise it to the third power, you just get the y. We've been doing that. That would have been nice information starting off. But anyway, let's just jump in. Let's see, resolve this mess here. We have y equals, this is our original, y is equal to the square root of x minus 4. Let's switch the x's and the y. So x is equal to the square root of, this is supposed to be a 4 here. Why on earth did I write a y? X minus 4. So similar. All right, anyway, switch the x's and the y's. We get y minus 4. So now what do we have left? We're going to go ahead and square both sides. So we're going to raise this to the second power. We're going to raise this to the second power. We get x squared is equal to y minus 4. Get the y by itself. We're going to add the 4. Add the 4. You get y is equal to x squared plus 4 now because they cancel. This is your inverse now. So your inverse, remember, once you get the y by itself, that's your inverse, x squared plus 4. We have everything we need. Now, let's address the elephant in the room for a second. the original started off with the square root. And remember, whenever you have a square root in a fraction, there's a big chance that it's going to have a restricted domain. Your domain is not going to be negative infinity to positive infinity. So what is our domain? Well, you know the inside of a square root cannot be equal. It cannot be less than 0, right? It has to be greater than 0. Can the inside of a square root be equal to 0? Yes, the square root of 0 is definitely 0. So we're going to take for the domain, we're going to take the inside of the square root and set it greater than or equal to 0. So let's go ahead and add 4 to both sides. You get x is greater than or equal to 4. This is your domain of your original. So that's going to be helpful to us. What about the range of our original? So, I want to see something. I want to, yeah. We got to get the domain of our inverse, right? If we get the range of our original, we can get the domain of our inverse. Okay. I'll level with you. This is a square root, right? So you can imagine for a second that we normally start off here. And this is a little callback from the original chapters. We have x minus 4. So remember, we do the opposite of what we see on the inside. So 1, 2, 3, 4. We're actually going to have that function over here. This is the original function right here. What is your y doing here? Your y starts off as 0. Remember, this is your y-axis. So when you're looking for a range, look at your y-axis. What is your y equal to here? Your y is equal to 0. And is it solid? Yes. So this is for range. Your y is solid right here. So it starts at 0. And then what is your y doing as you go up? Your y is increasing to the moon. So that's 0 to infinity. So the range of your original is 0 to infinity. So the domain of your inverse has to be 0 to infinity, which is greater than 0. And now we're going to go ahead and put our inverse function that we just found right in there. So do you remember? Take a look at our inverse function. At first glance, we don't have any fractions and no square roots, right? That's true. This is a parabola that's shoved up 4 units. So normally, just really quickly, this U shape will look like this. This parabola looks like that, right? But because the original came from something that didn't have a domain and range as negative infinity or positive infinity, you can't just put a U shape here. Actually, it's going to be chopped up just a little bit. We can't have any negative values because it conflicts with the range. And you're gonna see as we go forward, you're gonna see how that graph looks like. They basically chop off this left-hand portion because everything over there is going to be negative. And just really quick for kicks and giggles or whatever, right? Let's graph the original thing we had in blue just a little while ago. And let's run a dotted line going straight through the origin just like that. Look at that. Mirror images of each other. So you can't go wrong with these methods I'm giving you. I promise you they're going to be very helpful to you in the future. All right, fantastic. Okay, so we need something to look like our beautiful little rough sketch there. That's the closest thing to it right there. Bam. Okay, what is the domain of your original, which is basically the range of your inverse? Well, we stuck with the original. The domain of your original is x is greater than or equal to 4. They want interval notation. So it starts at 4 with a bracket because it's included. It starts at the 4 and goes off to infinity. So 4 to infinity, greater than 4. All right, well done. And now what is the... Oh, I didn't even read that. Okay, the domain of f is the range. Okay, I didn't even read it. I guess because I knew it was correct. Yeah. You don't want to choose that the domain of the original, which is f, is the domain as your inverse. No. The domain of your inverse is always the range of your original and vice versa because you switch the x's and the y's, right? You don't want to ever keep your x's the same. Remember, domain is x, range is y. You want to switch them and mix them up, but not mix them up so you get it wrong. You know what I mean? You know what I mean? Okay, the range of f should be the domain of your inverse. So we got to choose B. They're trying to get you. So look out for that on your exam. And what is the range of our original? Well, we figured that it's going to be 0 to infinity. So we can go ahead and choose 0 to infinity, or type in 0 to infinity. And that's an excellent day. And I think we got them all correct. Yep, that's the last question, question number 18. That is it for the inverse. If you have any questions, you can type it in the comment section. I'll get back to it. I'm not doing anything for a little while. I enjoy making these videos. I will see you guys in the next video, and thank you so much for watching, and thank you for subscribing to my channel. All right, talk to you later.